So hello everyone. So we have come midway into our course, and today we'll be starting off with a new chapter on torsion. This is chapter 6 in your textbook. So let's get straight into the motivation and see what is torsion and why would we want to study the mechanics of a torsion. So in the second chapter, as the author says in your textbook, we saw how the three steps of 2.1 form the basis for the analysis of simple problems. Okay, and then we have, after those chapter second, we have seen how these three steps are used for more involved and rigorous analysis. Okay, now we are ready. Now we have all the tools to actually apply them to real engineering problems. I mean, if you remember and recall the problems which you had done in chapter 1, okay, they were more or less like how you had done it in your APL 100 and perhaps in your school education before that. They weren't real mechanical or real engineering problems, and the problems which you start doing now in this particular chapter are more sort of towards the side of engineering, the real life problem, as they say, and hence it will be more fun to apply the ideas which you have learned into those problems. So let's consider the problem of twisting or torsion. So okay, so we consider twisting or torsion. A slender element subject to primarily to twist is usually called a shaft. Okay, just like a bar is primarily to extend or compress, beam is primarily about bending, the shaft is primarily about twisting. Okay, so this is one of the important members which you learn about, and most likely in your machine design course you might learn about designing of shafts. Okay, so twisted shaft plays an important part in many mechanisms, and a major use of such shafts is in the transfer of mechanical power from one point to another. So you have this figure 6.1 and 6.2, and this is somewhat used in an automobile. So let's briefly discuss how shaft works and where is the torsion, and finally why would we want to study torsion. Okay, so this figure 6.1 shows the schematic of a power transmission in an automobile. So you have a compression in the cylinder, compresses gas, which exerts compressive force on the piston. Okay, and piston rods tend to twist and bend. Okay, this is also there, but we primarily focus on twisting. The crankshaft, the torsion is transmitted by the drive shaft to the rear gearbox, which in turn exerts torsion on the rear axles. So I do not know whether you will ever have a course in IC engines or automobile, but for the sake of discussions over here, we will have to understand how this works. So let's consider a IC engine, which is called an internal combustion engine, and it is called an internal combustion engine because the combustion happens internally, okay, in the inside the engine. Okay, so this is the piston of your engine. Okay, you have this over here, and then there is a air and fuel mixture which gets over here. Then because of this air fuel mixture, combustion happens over here. The process of combustion happens. This combustion then pushes this piston down. Okay, and then there is this crankshaft assembly. Okay, it's called a crank mechanism, And the way this works is that as it moves down, there is a certain rotation over here. Okay, and again then it would go up and then it would complete the cycle. So the linear motion of this piston will convert to a rotational motion over here. Okay, and this rotating part is connected over here. If you look, okay, there is a crankshaft over here which rotates like this. So you can look up a video for an animation of IC engine, okay, where this can be discussed in slightly more detail. I mean, there is a timing at which this combustion happens, then it comes down, then it goes up. So it's a cyclic process and it's all timed well. Okay, how when the air fuel mixture will be added for combustion and so on. The eventual part is the linear motion of this piston gets converted into this rotatory motion over here, and of course there is bending because you also have a force which is applied like this, but overall we want to focus on torsion only. Then this is connected to a drive shaft. Okay, so I see, so most of the cars which you see around you have the engine in the front, so they are called a front driven car. Okay, so the shaft of this the drive shaft also, because of this rotation, the drive shaft rotates. Okay, and once that happens, it this rotation, this there is a rotation like this. Okay, in the sense it is, there's a twisting motion over here, and because of this there is a sort of a gear assembly over here which transmits this rotation into another rotation but in a different way, like this happens like this for the axle. Okay, so there is this sort of this gear assembly over here which will do that transmission assembly, and eventually when this axle experiences torsion or it starts to rotate, then your vehicle will move. So the power comes from the front, goes to the wheels at the back, and because of that your vehicle will move forward. Okay, so this is one example where torsion acts, and you can see that wherever there is a rotation which is happening like this, there is a torsion. Okay, and also like this, there is always a torsion, and that is very simple to visualize as well. Hold up your pen using two hands. Okay, I mean, assuming that you are a right-handed person, which 93% of the people in the world are. From your left hand, you hold one end of your pen. From the right hand, hold the other end of the pen and try to twist it from the right hand, keeping the left hand stable. Okay. As you try to rotate it, you will see that you are actually applying a twisting force, something which you are trying to twist. And if it's large enough, then your pen will actually start rotating, overcoming the friction which your left hand is acting. So that's very easy to see why rotation and twisting are accompanying each other in over here. So that is what you see, and every time you have twisting or torsion, that part is pointed out over here. Okay, that's the first part of where an engineering problem has torsion acting. Let's look at the other case, which is about a lathe machine. So you must have done this in your workshop course. If not, you should open up your video browsing software, whichever one you use, and you should look at this turning operation and lathe. Okay, so if you remember what this does, sorry, okay, so what this does is that if you have a specimen, say of this diameter, d cylindrical diameter, and you want to eventually have a specimen of smaller diameter d, either full or in part, you put it near the cutter, cutting tool, and then you give something which is called a feed, and then you would eventually have this turning operation. The chips would fall off, and your workpiece will get reduced in size. Okay, so this is something which you have done for most probably. If not, I mean, you can please look up the video right now before you move ahead. Okay, so the way this works is also quite simple. You have your cutting tool. Of course, it's a very sharp and hard object. Then you have your workpiece, okay, which is fixed like this, and this is clearly rotating. If you observe your video, or if you have done, you will observe that there is a torsion and bending. Torsion because it is trying to rotate, and as soon as you have a rotation with those connections, there will be torsion, automatically twisting sort of an effect. And bending because this tool which you have will also apply a force like this, so there will be also a bending over here, just like you had it over here. In this case, the force would be acting like this also, other than the rotation which is happening. So anyways, so once you have this, so the idea is that this rotates, okay, and this rotates because this shaft rotates. Again, rotation automatically means torsion. And then you have, and this shaft rotates because this wheel would rotate, and then this would rotate because there is this belt which is in tension. And perhaps you have done this problem in your APL 100, or a similar problem where there's a belt which is moving, a conveyor belt sort of a problem. And the only difference is that this is small, this is large. Okay, of course the speed and power have an inverse relationship, so this will be there, and this will also rotate. This rotates because this torsion, the shaft will again be rotating, and this rotates because a motor which takes electricity makes it rotate. Okay, so the motor causes this rotation, having torsion in the shaft, and which causes this tension in the belt. Obviously, there will be friction acting between the belt and these pulleys, and this causes a rotation in this shaft, which will have tension, sorry, twisting effect on this shaft, and your workpiece gets cut. Okay, so these are two examples where torsion acts, and the mechanics of torsion. Why are we? I mean, this is just knowing where the torsion acts. Why should we study the mechanics of torsion? From a design perspective, from a design engineer's perspective, it is to decide what should be the material and size, or say dimension, in the sense the cross-sectional area of this drive shaft, so that it can rotate at a certain speed, okay, and supply a suitable power to your vehicle without failure. Okay, how would you do that? You would have to find the stress using the elasticity concepts. You would find the stress tensor at any given point, convert it to the principal system, okay, and then use those principal values to test your failure theories about this, whether it will be able to sustain this or not. The same would happen over there. This cutting tool would apply a lot of force on this workpiece, okay, and hence this entire system should work properly for any designed feed you want, you desire. Okay, so most of the lathe machines have a range of what should be the feed rate. Feed rate is essentially how much this tool or the workpiece is going in per unit time. Okay, so that is what a feed rate is. So it must also not break. So this is a designer's perspective of studying mechanics. And normally you don't want your shaft or the axle or the shaft of the lathe machine to yield, which is considered a sign of failure in most theories which you learn in your designing course. So that's the reason. So your design course actually will begin assuming that you know sigma 1, sigma 2 and sigma 3, okay, so that you can put it in a criteria of failure. Your job and our job in this particular course is to arrive at a state of stress so that this can be found out. Okay, so we want to find this for twisting or torsion. Okay, so that is a good sort of motivation for torsion, and what we are primarily interested is when you in say a torsional spring. So you have learnt about a linear spring, okay, which will deform if you apply a certain load, and then it will have a stiffness. There are also torsional springs. I mean, you can see the working of a clock, for example, okay, the clock or those toys which used to have those springs into it, okay, many of them worked on torsional springs. So the idea was that you used to apply a twisting moment, and then you would get a desired angular twist of the shaft. That angular shift is the angular twist is the rotation which you would want it to cause. So it was the same thing as it was in a linear spring. You apply a certain force, you want it to uh, compress or extend to a certain degree, and the same would apply for a torsional spring as well. Okay, so this is what you want to do, and let's sort of begin this analysis using the ideas which we have learned before. Okay, so coming to this section 6.2, which is the geometry of a twisted circular shaft, we consider a uniform circular shaft made of isotropic material. Okay, so we have already seen what an isotropic material is before. Now let's look at figure 6.3a. This shows a circular shaft loaded only by twisting couples empty at its end. Okay, so this is very similar to you holding your pen and trying to twist it from one end. Okay, you are applying a twisting moment. Okay, and the other end is fixed, so automatically for it to be in equilibrium, the other hand is also applying a twisting moment in the opposite direction. So it's a twisting couple empty at its end, and the cylindrical coordinates are r, theta and z. You would know where the origin is. It's at this end. This is where the origin is, and you have r, you have theta and you have z. Okay, the length of this shaft is L, capital L, and we'll see how we can study the deformation in this twisted circular shaft. Okay, let's look at 6.3b, this figure. This shows the fact that equilibrium requires that each cross section of the shaft must transmit the twisting moment empty. So if you virtually cut this at this place, virtually, okay, not really, and it's the same idea. I mean, you want to make this hypothetical cut so that these internal twisting moments actually become external, and you can apply now the equilibrium to find that value. So this is how the MT would be shown for each section, the section 1 and section 2. And as you see, the sense of both of them are always opposite. So this goes up, this goes down, this goes up, this goes down, and they among themselves also have to act in this way. So this is just like this beam which we had taken a virtual cut, and what would be the shear force over here? Two sections, one section, so That's how it would act. Okay. And similarly, I mean, if it was an axial one, you would have something like this. Okay. So once this is sort of figured out, um, we now start our consideration of possible modes of deformation by isolating from the shaft a slice delta z, okay, in length with faces originally plane and normal to the axis of the shaft. So you want to now consider what are the possibilities of deformation in a shaft, and for that we have taken a slice this delta z you see over here, and I mean that's what is shown in this figure. So now we take this slice from somewhere near the middle of the shaft. This is an important part, that you want to take it not from somewhere close to the boundaries but somewhere from the middle of the shaft, so that you are away from the end effects, okay, the boundary effects which we have discussed when we were discussing Saint Venant's principle in the earlier part of this course, I think in chapter 5 somewhere. So that's the whole idea, and most of the time you would want to do this. You always want to stay in the bulk away from any boundary, so that if there's any possible end effects, you can that will not affect your understanding. So that is why we do this. Okay, now before proceeding further, we observe that since any other slice taken from this region will have an identical original shape and will be subject to the same twisting moment, we can expect it to have the same deformation. That is, the pattern of deformation will not vary along the length of the shaft. Okay, so this is what we say. Assuming this delta z which you have taken is from over here. Okay, this is delta z. Again, away from the boundary so that it's not affecting the boundaries don't have an effect on what we do. Similarly, if you choose any other part, say this one, delta z, this will also have the same pattern of deformation as the previous one. Okay, so this is what they say by when they write the pattern of deformation will not vary along the length of the shaft. So this will always be empty in this direction, this will always be empty in this direction, and any change which happens in the deformation for this originally undeformed piece of the part of the shaft, the pattern of deformation will not change. In the sense, the value may change, okay, but I mean the sense and the patterns will remain the same, and we'll see that slightly in more detail. So our aim is to deduce a plausible mode of deformation for such a slide. What are the possible modes of deformation for a slice like this of the shaft? Now in this process we shall appeal to one of the most powerful arguments of science, the argument of symmetry. And I request you to be very careful about the language which I am using, which the author in your textbook is using. Okay, so none of it is actually hurried. It's all a well thought of idea. So I request you to pay attention and perhaps understand it to a level where you can apply it yourself to other things. Okay, now because of its simple shape, the circular shaft is particularly vulnerable to symmetry arguments. Remember, in the this thick cylinder problems, there was also a symmetry because of its shape, and a similar thing will be happening over here as well. So that is one of the other reasons we started off with a circular shaft. Okay, and most of them are circular anyways. In engineering problems, most of the shafts are circular. Okay, so you have this figure 6.4, which has a originally straight radius OA. So you can see this radius OA, okay, originally straight, shown by the straight line. this has deformed or hypothetically deformed. I mean, this is what we are exploring. How will this deform? Okay, into OA dash, like this curve. Okay, and this is very similar to how we had considered this hypothetical deformations when we were trying to make this argument that a sigma x stress cannot produce a gamma xy strain. Okay, so we had hypothetically deformed it, and then we rotated it, and then we said, well, I mean, this is contradicting something, and hence the only way this is possible is when gamma xy is 0. So you remember that? So that was a hypothetical deformation which we assumed, and the similar idea we are using over here. Okay, so OA has deformed into the curved line OA dash. That's one thought process. Okay, let this line deform like this, OA dash. Since the material is isotropic and the slice has a full geometric circular symmetry about the z-axis, we must then conclude that all radii are deformed into identical curved lines. So it's not just OA. If this is true, okay, if this what you see over here is true, it's not just OA, but say another OF, which should deform exactly in the same way. The reason is it's an isotropic material and it has a symmetry, a very strong symmetry for that matter. So any line segment which you draw like this will deform in the exact same way. Okay, so the same curve, this curve will trace all of the lines. Okay, so I'm just removing the other ones. Let's keep only two of them. Okay, furthermore, these curved lines must all lie in a plane. That is, the ends of the slice remain plane during the deformation. So since this line, originally line OA, lies on the plane, OA dash will also lie on the same plane. I mean, it will not, this curve will not be drawn in the z direction. It will be only drawn on this plane. Okay, and so will all the other lines which you draw. Okay, so that gives us a confidence that if this was originally plane, it will continue to remain plane after deformation. So it's not like, say, you have a bed sheet, okay, which may be like flat like this, but after maybe when you get up in the morning, there are these, okay, these sort of deformations. I mean, in the thickness direction there are these small structures which form after deformation. So this is not happening over here. All the deformations are acting in the plane itself. Okay, so a plane surface remains plane. Okay, and we can demonstrate this by a simple symmetry argument. So let's see how that uh, happens. Okay, suppose that one end of the slice bulged out. Okay, so what we are doing is we are assuming that one end of the slice bulged out or dished in, meaning, say, this flat. So I'm trying to now see from this side. So this is my eye and I see it like this. Assume that, so I'm seeing like this. Okay, I hope you know how to see this. Okay, you must have learned it in your first year. So I don't know, it's called a front view. So if this dimension is, if this diameter is d, so you would see this as d and this would be delta z. Okay, now by the, we are making the symmetry argument this way, that suppose that one end of the slice bulged out or dished in. So either it dished in one end or it bulged out. So I'm just taking one of it which is dished in. then symmetry would then require that the other end do the same. Okay, in the sense, if this has bulged in, the other end should have also bulged in. Okay, and that is a problem. Because the hold on, but then the other end which you have, say the slice which is next to it, okay, so this was delta z, okay, and the slice which is just below this, I mean, I'm not putting a size to this, but this top surface of this must also bulge like this, right? This would happen because, I mean, this surface and this surface are the same. So if this is dipping, this is coming in, so this must also come in, and this cannot happen because you will not be able to fit in lots of so to say, you will not be able to fit in all these pieces. So let's look at this in another way. I mean, let me find out another easier way to make this argument. So symmetry is hard. Okay, so let's start with this. We can demonstrate this by a simple argument. Let's take these uh, two parts of it. I mean, what do I mean? I mean, this is one slice of it, this is one slice, this is a second slice. Okay, so I'm just showing you the front view of this, but separately, obviously. Okay, so this is the whole thing, that if one end of the slice bulged out, the other end will also bulge out. Okay, why would this happen? Because of the symmetry. I mean, there is no distinctions. You see, there is a symmetry which acts on this in the radial direction. So whatever happens on one face, the same will happen on the other side. Okay, and this cannot happen really, because if this is bulging out, then this would need to dish in. Sorry, this would need to dish in, and it will not be, if this is dishing in, this should also dish in, and it's a problem because all your slices 1 and 2 must deform in the same way, so this is not possible. Okay, so they will not be able to fit together, that is what they mean. Now consider the other case. Let me draw this. Okay, again 1 and 2 as usual. So this time I am telling you that if one faces dishes in, say this one, the other face of this slice will also dish in. Okay, and this dishing in automatically means that this has dished out, and if this has dished out, this must also dish out. Okay, so this makes it very hard to actually hold this collection of slices together. And first of all, this cannot happen, I mean, by the same logic, I mean, both of them should have the same deformation pattern, so this is impossible. The other way you can make this, let's give it one final shot, and I think this should definitely work. And this is something, I mean, you see, the way we are going about this, you will also have to do these thought processes and see which one of them most closely matches what is written in your textbook. Okay, So if this has bulged out, the other end would bulge out. Okay, now this was one, and because both of them have to show the same deformation pattern, so this will also bulge out and this will also bulge out. So you will not be able to hold this, so it would be impossible to fit a number of such deformed slices together. You see these bulging, so it seems this is the most accurate description of the symmetry argument. Okay, so this last attempt which we made was the most accurate description, so I would request you to hold to this one for over here. Okay, so this is, this is how you have to proceed when you read a textbook. You might not get it at one go, but you have to, because if your instructor doesn't go through this thought process, everything will seem very straightforward to you. Oh well, this is obvious, that is obvious, and so on. So must go through all these thought processes, give it time, and convince yourself that you are actually right. Now, so it is impossible to fit a number of such deformed slices. How? These. So the third one would also be like this. Okay, so this dashed lines would not be really helpful in forming a complete continuous shaft. There are clearly discontinuities like this. Okay, so thus we conclude that when a shaft is twisted, its cross sections must remain plane. So this means that you cannot have a bulging or a dipping in on any face. Okay, that was the first part. Okay, let's now consider a slice shown in the upper part of figure 6.5, this one. Let me just make this big because it seems there is no maths over here, just a lot of talking and thinking. Okay, so we are seeing this upper part of figure 6.5. We focus our attention to this section. Uh, so you have drawn this section HOABCJ. HOABCJ. Okay, this is one section which you have taken, which is planar before deformation. So this HO, okay, this shaded part is one plane. Okay, before deformation. Now when the twisting moment MT is applied, okay, this section will deform into some distorted shape. So let's assume that distorted shape is H dash, O, A dash, B dash, C and J dash. Okay, and clearly this distorted shape is no longer a planar, okay, because of these curves which you have. Let us tentatively assume that the curvatures of line H dash O A dash and B dash C dash B dash C J dash are as indicated in figure 6.5. So this is just an assumption that these curves H O A and B dash C J dash are like this as they are shown. Okay, so I'm just removing it, but for so this is just a tentative assumption and we want to see whether this assumption is correct or not. That's what we are trying to do over here. Okay, so we can show, however, that this assumption leads to a contradiction by considering in the lower part of figure 6.5 the very next slice. So this is the very next slice, the one which is just below. If this is your shaft, say this part is like this and the part which is below is over here, just below this is over here. So how do we know it's a contradiction? Because if this JCB, which was originally straight in this one, okay, JCB would mean this is like this, and B dash CJ dash would then become like this, okay, because this part is just below this. So B dash CJ dash would also follow the same trajectory. like this. Why is this a contradiction? Because we had just discussed that any part of the shaft will show the same deformation pattern. So the top part was having a curvature like this, and the bottom part and the top part of this one, this slice, is showing a curvature which is opposite to like this. So this is a contradiction. So that is what they say. There is a contradiction of this assumption. So since this element is subjected to the same deformation as the element above, we expect the diameter A1O1H1. Let me remove this. We expect that the diameter A1O1H1 dash with the same shape as A dash O H dash. Okay, so this is what should happen, and because of this argument what we were getting is something like this. So this was incorrect. Okay, so such deformation however would violate geometric compatibility, because I mean when you take the bottom face of this slice like this, you are saying that the top face of the next slice has to go by this because of the geometric compatibility. Because if it is not there, then there will be a discontinuity in your displacements, which you are not allowed in this course at least. Okay, so this would violate geometric compatibility since the curvature A1 dash O H1 dash and B dash C J dash have opposite sense. So it would be impossible to fit these two elements together when deformed as shown. Okay, so that part is out. That this assumption, this tentative assumption which we had made was incorrect. Okay, now since the curvature assumed for B dash C J dash in figure 6.5 has led to a contradiction, we next make the tentative hypothesis that B dash C J dash has the opposite curvature shown in figure 6.6a. So let's move to 6.6a. Okay, and let's see how is this opposite. Okay, so you are trying to compare this with this. So the top face has a plane, a straight line HOA. Okay, and H dash OA dash seems to be common, but the way the bottom face deforms is of a different sense. So please look at the bottom face of 6.6a and the bottom face of 6.5a. Please notice how B dash C J dash are shown. I'll just extrapolate, I'll just exaggerate it so that you can see the sense of it. It looks like this: B dash C J dash. Over here it looks like this: B dash C J dash. So the sense of this is opposite. So the curvatures are opposite. And what forces us to do this? Our earlier assumption failed. So we are taking the opposite curvatures now just to see whether it works, whether it fits this symmetry argument. So this would permit matching adjacent elements. Now can you see that if you have a curvature like this at the bottom face of this slice, the slice next to it, the slice which is just below this, okay, this one, how would it look like? It would look like this, I guess. Okay, sorry. Okay, yeah. So the bottom would look like this, and what this would do is it would help you. I mean, and this, if you see, is the same as this one, A dash O H dash. Okay, bulge going up, bulge going down. So this is the same curvature which you would have. So that is what they say, that this would permit matching adjacent elements. So it seems this will work, at least the case which we were doing. Okay, so this is for the upper face of slice just below. Okay, this one, and this is clearly this one. Okay, now nevertheless, this pattern of deformation also leads to a contradiction. Well, it wasn't lived for a very long time, so let's see where is the contradiction. It seems all of it is matching. There is a geometric compatibility. So where is the contradiction? To see this contradiction, you will have to see this. We rotate the element in 6.6a, okay, about 180 degree, about the axis x dash. So I'll just rub off these parts. And let me see. Okay, this is better, because we have already established that geometric compatibility is fine if you do this. So let's focus on this one. Okay, now to see this, we rotate the element we rotate the element in 6.6a about the axis xx. So where is the axis xx? Okay, here it is, which is perpendicular to the element HOABCJ. Okay, now after a rotation of 180 degrees, the element is upside down as is shown in figure B. So H should be here. Okay, so one thing is that this plane HOABCJ should continue to remain a plane. Only thing is this H will, after this 180 degree, will come over here. So that is what has happened, and O has come up over here. So there's no problem in this plane. It remains a plane. It's just that the points have shifted as expected. Now you want to compare 6.6a and 6.6b. One of the other things which we have to do is we have to also rotate this deformed uh, surface. I would not call it a plane. H dash O A dash B dash C J dash. You want to rotate this, so H dash should come over here. Okay, it's a 180 degree rotation. So this point will come over here, that it has come, and similarly A dash would come on the other side over here. Okay, and that's how you can do. So clearly, I mean, this is passing through the center of this original undeformed plane. So this is how the deformed geometry has been formed after this rotation. So after the rotation, you have pointed out all the undeformed and the deformed points on this. The elements are of identical shape, actually the same shape and material, and are subjected to identical loadings. I mean, even after this rotation of 180 degrees, the loadings are identical in this case when you apply. Therefore, they should have identical deformations. But the curvatures of diameters in the two elements are of opposite sense. Look at this curvature. It is like this, the top face, and over here it is like this. So the curvatures are of the opposite sense. So this assumption which we have rules out our possibility, our assumption rules out our assumption that the curve which this particular deformation will work. Even though it is fitting the geometry, it is not satisfying the symmetry argument. because after deformation it is still experiencing the same load in the same sense. So why both of them should have a different uh, deformation? So that is also ruled out. Hence, we have tried everything, right? We took two possible curvatures and there is no other way, frankly. So the only possibility left out is this. So this is what we are forced to. After these arguments, okay? So please go through this struggle, this thought process which I am going through, and you have to read it again and again to actually be convinced by this. This gives you a better point, better view of the world as such, I think, to be able to think about in different ways. Okay, so straight diameters are carried onto straight diameters by the twisting deformation. This is the most straightforward stuff. This HOA straight line gets carried forward to H dash OA dash as a straight line, and this BCJ gets carried forward to BCJ dash as a straight line. So this will be both having a geometric uh, compatibility, and it will also not violate the symmetry argument if you try to rotate it. I mean, please try to rotate it by 180 degrees, just like you did in the previous case. Okay, after this 180-degree rotation, well, the points have changed, but you see the sense of deformation remains exactly the same. Okay, which it should have. So this sort of, through this we can conclude that the plane surfaces will remain plane, okay, during twisting. The deformation, this is how it will happen. So we'll continue and take off from here on. We want to now quantify this deformation through a shear strain, and we'll do that in the next class. Thank you.